3 lectures on fundamental physics. I'm going to cover this first one, while Richard is going to cover the other 2 lectures. And first of all, I would like to start by giving you some fundamental references for fundamental physics, which I think they are nice references to have at hand if we want to go and explore this topic here. So I'm putting here some general reviews. I'm picking, let's say, just some of them. Of course, there are much more. But I wanted to start with this. And I'm also putting them here in a chronological order. So the first one is this one, about testing general relativity with a low-frequency future space-based detector. And it's from John Gare and collaborators. And here we are in 2013. The second review I put here, it's from Emanuele Berti and collaborators. And it's about testing general relativity with the present and future astrophysical observation. So this is a very nice and general review, especially also for modified gravity theories. So I'm going to show you a plot, for example, which is taken from this review. And if you saw already some talks about this topic, you're sure you've seen as well already. And here we are in 2015, so a very nice year for gravitational wave people. And then more recent review. We are here in 2022, and this is a review about new horizons for fundamental physics with Lisa. So this is about fundamental physics. And in 2023 here, I'm putting the waveform modeling for the laser space interferometer. And this is a review of the waveform modeling working group. But I'm putting it here because there is a section which also touches topics of waveform modeling beyond GR. So it might interest you as well. And finally, here the last review I'm putting is the LISA definition study report. So it's our red book for LISA. And they are listed all the science objectives of LISA, and we have the fundamental physics science objectives, which is SO5 for fundamental physics. So fundamental physics feature very prominently among the LISA objectives, and one of the goals of the mission is to probe fundamental physics. So in this talk, we are going to see how this could be possible for our space interferometer. So I'm going to start by presenting, let's say, some motivation to go beyond general relativity and how, why we want to probe fundamental physics and in general relativity. So here, some motivation. I think it's a nice overview to have in mind. General relativity is the best description of gravity that we have so far, but we have some open problems related to fundamental physics, and in particular to general relativity. So we have, for example, that general relativity is not renormalizable in our quantum field theory sense. In particular, we have the Planck length, which is a very small length with the corresponding very high energy scales. And we can see that at this length here, both quantum field effects and gravity effects become relatives, and both theories break down. So we have this fundamental problem here for our 2 pillars, let's say, of fundamental physics. So we can think that GR has to be somehow a low-energy theory of some other theory. Other problems that we have, they come from cosmological observation, as, for example, the existence of dark matter and dark energy. So we could ask ourselves, is it possible to explain this cosmological observation by considering some GR modifications? We have, for example, some pathologies in the sense that from a mathematical perspective, we have the black hole singularities, and also, for example, the black hole information loss problem due to the Hawking evaporations. And another motivation to, let's say, modify GR or looking beyond it is that we are now going to explore the strong field regime of gravity. So before gravitational waves, basically the strong field regime of gravity was almost unexplored. And with gravitational wave, we are also going to explore this new regime. So it's, let's say, we can ask ourselves, is GR also is going to work at these scales here? Because we have seen also historically that every time we explore a new scale of investigation, things might not work. So this is a fair question that we might ask ourselves. And in particular, with LISA, we also are going to explore a new classes of sources at low frequency, so there is a whole new sources to explore there. Okay, so these are some physical motivations that it's a nice overview to have in mind every time we ask ourselves why we should test general relativity. But there is one general here, that I put it here, I don't know if you can see it, it's very low, but basically we have general relativity, we have our theory to describe gravity, but we need to test to see if it works and if it's right. And in order to test general relativity, what we need are some alternative models to be compared with GR predictions. So this is a thing that we can have generally in mind. We need to think about other models to retest again GR. Okay. So this is the overview of the motivation. And now I'm going to say how can we then test general relativity. And I think there are two, there is a nice approach to this, which is by classifying this test by considering two different approaches. And one is considered the bottom-up approach, where, why bottom-up? Because we go from the bottom, which means we are looking at our observation. So we are looking at the phenomenology that we want to study. We look at some quantities that are the most appropriate to describe this phenomenology. Then we devise a particular parameterization of this quantity. And typically we can see that this parameter can be related to some violation or modification of some GR properties. Then we compute some observables in terms of this parameter. So what I'm going to observe need to be expressed in terms of these parameters. And then I'm going to perform some observation and experiments in order to set bounds on this observable here. Okay, so here we are starting from the observation and we set bound on some new parameters. Some example of this approach here are, for example, some parameterization. We can look by starting from, for example, to isolated body. So we have what is known as the parametrized post-Newtonian metric. And this has been used, for example, for solar system tests. We can think about some parameterization of some black hole metrics. Here, just some examples. This is for isolated body. Then we can also think about some parameterization of the motion of some compact binaries. For example, we have the parameterized post-Keplerian expansion for binary pulsar. And here we are putting some parameterization of the motion of the compact binaries. And then we have also the parameterization of gravitational waves. You cannot see. Okay. And for example, here we have the PN formula for the phase of our gravitational wave. And we can think about some deviation of the PN parameters. And then there is the more refined parameterized post-Einsteinian expansion. And here, basically, one takes our gravitational waveform that we have in GR, and we modify with some parameters the amplitude and the phase of the gravitational wave. And then we go and then we look at bounds on these parameters. So I'm not going to focus on this approach here now because it's going to be covered by Richard. I just put it here to have the picture of this approach in mind. And then there is the second approach, which is the top-down approach. Well, and here we go from the top to the bottom, let's say. What does it mean? It means that we are considering some GR modification, possibly inspired by some physical considerations. From this GR modification, we work out some observational consequences, and they are going to typically depend on the parameters of these GR modifications. And then we are going to set the bounds of these parameters coming from observations again. So here we start from the theory, and we conclude which are the observational quantities that consequences that we have for these GR modifications. And here some remarks, because in this approach we can see that in most cases what we are looking at are tiny modifications. Okay, where the parameters has to be small to exist in data. Another problem that we might have is that often it might be difficult to disentangle these GR modification from simply some physics effects which are then poorly known. For this way, we often say that black holes might be better than neutron stars for this, because let me pass the term, but black holes are, let's say, cleaner with respect to neutron stars. And also, when possible, what is best will be to find completely new effects, which are known as smoking guns for detecting deviation from GR. An example would be, for example, the dipolar radiation. So we know in general relativity we have dipolar radiation. So if we detect a dipolar radiation, that will be a smoking gun for a new effect, which is not present in general relativity. Okay, so these are the two approaches. And I'm going to focus on this top-down approach here, when we need to consider some GR modifications. And the question is then, how do we modify general relativity? Okay, so forgive me. I know maybe you already know all of these things, but I prefer to be clear and to explain all the connections. Okay, I was saying I'm preferring to be boring than not understandable. So, okay, here we have the Einstein field equations. We have our Einstein tensor, which is built with the Ricci tensor and our Ricci scalar. Then we have a cosmological constant, the cosmological term with our metric tensor, and the source term, which is a stress energy tensor for the matter fields. And if we are in vacuum, for example, this term here is simply 0. We can derive the Einstein field equation, for example, from action principle by going to consider an action. So, for example, we can separate these two terms here, where we have both the metric tensor and some matter fields. And here, there is here the Einstein-Hilbert action for our metric tensor and the action for our matter fields. And by varying this action with respect to our metric tensor, it's possible to obtain our GR equation. Now, I'm writing all of this because our Einstein equations satisfy a uniqueness theorem, which is the Lovelock theorem, which is basically this one. And it states that if we are in a 4 space-time dimension and we consider a tensor with all these characteristics here, so for example, rank 2 symmetric, divergence LS free, which is constructed only by the metric tensor and the derivatives up to second order, with this invariance here, which is the homomorphism, basically what we end up is that the Einstein tensor is the only one that satisfies all these properties here, plus a cosmological term. And these are the uniqueness theorem for our Einstein field equation. So the original question was, how do we modify GR? And a typical approach is to consider this theorem and start to break the assumption of this theorem here. So this is the plot I told you before about the view of Emanuele Berti and collaborators. And we can think about modifying GR by breaking the assumptions of our Lovelock theorem. So here, basically, forming assumption of the Lovelock theorem. If you start to violate them, you start to classify new modified gravity theories. So, for example, here there is the weak equivalence principle violation, the diffeomorphism invariance violation, which gives rise to massive gravity theories, Lorentz violation. You can consider extra fields and end up with this type of theories here, or higher dimension for our theory. Now, you can see that we can give rise to a lot of modified gravity theories, but it has been shown that for the mass majority of a lot of modified gravity theories, they can actually be reformulated as general relativity plus new fundamental fields. So here I'm going to focus on these theories here, where we have GR plus some new fundamental fields, and in particular I'm going to focus on what are known as the general scalar tensor theories, when our new fundamental field is new scalar fields. So you might ask yourself, why scalar? Well, they are ubiquitous in all the theories of beyond general relativity and the standard model of particle physics. And also they provide, let's say, if we want to start modifying GR, they provide us with the easiest example, but also exciting example of new physics. So we are going to focus on scalar fields. And so what happens is that we start to modify the action I've shown before, our Einstein-Hilbert action, by adding some coupling constant. And here there is going to be a lot of interaction between maybe new fields and our metric tensor and so on, and then the action of our matter fields. So all the gravitational interaction are enclosed in this part here, and we have introduced some coupling constant, alpha 1, alpha 2, and so on. And here I'm writing two frameworks because we can think about this action in two ways. First of all, if we modify our action, what we should require is that this action will lead us to some field equations that are well-behaved. So, for example, we should require some well-behaved field equation with a mathematical consistency, with a well-posedness, which is a very complex task. So if you don't take care of this, you might end up with some pathologies, which are known, for example, as ghost or some instability that might arise. And this is a very complex task if you want to modify your action and prove this mathematical consistency. But another approach is instead to consider an effective action. Okay. And in this way, our effective action, what does it mean? It means that we are assuming that there are other terms of higher orders in this coupling here, but these terms are not relevant in the energy scales that we are going to consider. So basically what happens is that we are neglecting some terms. We are saying, okay, I'm just focusing on the action here, and I'm not going to check its mathematical consistency because I'm assuming that any problem might be cured from extra unknown terms. Okay, so this is a check that will have to be checked, let's say, in a second moment, and we can focus on our effective actions.
Yeah, question on this. I don't know, I never understood quite this going from full action to effective action. Like, how sure can you be that these terms exist? And I mean, this is a bit like, okay, let's throw all of our problems in higher dimensions, and I don't know.
So I will say that, I mean, you can find some full actions.
I'm sorry?
Full action in the sense that you can find some mathematical consistency. So it's a very complex task. Yeah, I don't know. Basically, you are focusing on your terms that are relevant at the energy scale that you are going to consider, and this is a problem that you might need to cure in a second moment. I don't know how to answer you.
Yes, it's a big deal.
Okay. So we are focusing here on, I mean, I think you can find with some fine tuning with some example also from known theory that are well behaved, some fine tuning for your action to be then mathematical consistent. Of course, it depends the case by case of what you're doing. Okay. So, general framework for modifying GR. Another property of GR for black holes is that in GR we have the Neuer theorem for black holes, stating that stationary and asymptotically flat black holes satisfy Neuer theorem. What does it mean? It means that for our stationary black hole in for dimension, it's only described by three parameters, which are its mass, its angular momentum, and its electrical charge. Then for astrophysical black holes, we can neglect the electrical charge, and we can end up by saying that in GI, the black holes in vacuum are described by the curve metric. Okay. But if we modify, so the question is, if we modify general relativity, do we end up also with some Neuer theorems? Do they hold beyond general relativity? And for example, if we focus on the addition of a new scalar field, what might happen in general is that our black hole is going to acquire some scalar profile. And in this sense, we say that the black hole acquires some scalar charges. Okay, so instead of having just these two parameters here, we are going to have another scalar charge. And if we consider the black hole as isolated body, we can see that we have this behavior of our scalar field centered on the reference frame of our black hole with some constant, our scalar charge that appears here, and higher order terms. Okay, this is wrong. Okay. And but however, okay, this is something that might happen in general, but it has been proven that for most scalar tensor theories, actually our scalar profile must be trivial. It means it's just gonna be a constant, so that we end up also with some no scalar theorems even beyond GR. So even with the addition of the scalar field, that we end up with some no scalar Hertz theorems. And this might be complicated if our goal is to test GR, because if you want to test GR by probing the existence of a new scalar, and you focus on black holes, what happens is that if your black hole satisfies a no scalar Hertz theorem, there is no way you can actually, let's say, test the presence of the scalar field in our universe. So how do we can we evade our no scalar theorems? We need to consider some couplings with some higher order curvature invariance. And in particular, it has been shown that if you focus on shift symmetric scalar tensor theories, when shift symmetry means that your are invariant with respect to this transformation here, you need to consider a linear coupling between your scalar field and this Gauss-Bonnet invariant, which is indeed some higher order curvature invariance. So if you consider this coupling in your action, you end up by evading the Neuer theorems, and your black hole will acquire some hair. But these hair are set of second type in the sense that it's not going to be an independent quantity. It's going to be a quantity that depends actually on the mass of your black hole. So here, for example, it's going to go with the inverse of your mass to some power of n. So what happens is that the more massive your black hole is, the more weakly charged it is going to be. Okay, and this is a fundamental, let's say, properties for Neuer theorems with scalar fields beyond general relativity. Okay, now let's see some examples then of some modified gravity theories that we have with some properties. And this is just to show you how the type of modified gravity theories that we have, we are plenty of them, and I'm not going to focus on all of them, obviously. But let's start with this one. So in this case, we have, for example, this action here. So our Einstein-Hilbert action with the Ricci scalar is modified in this case, and we are considering here coupling interaction between your scalar field, new scalar field, and your Ricci scalar. And then there are other terms for the scalar fields, and again, the action of your matter fields. So the simplest theory of this example here is what is known as the Brans-Dicke theory, where you need to choose a particular function of this scalar field, which is a constant divided by the scalar field. And this theory here presents no pathologies. It leads you to some second-order field equations. And also, it satisfies no scalar theorems. So this means that your black holes satisfy, do not have any scalar charge, and your black hole dynamics is the same of what you have in GR. So if you want to test Brans-Dicke with black holes, what happens is that actually their dynamics is going to be the same of general relativity, such as the waveform of binary black holes, for example. So if you want to test GR, you need to look at neutron star, which they actually present a scalar charge, which is going to depend on their equation of states. They emit the polar deviation, and you can test Brans-Dicke by looking at neutron stars. Another example is of f of r gravity, where you are modifying your Einstein-Hilbert action by considering some function of your Ricci scalar here. It has been proven that also these theories can be reformulated with the cases of before for scalar tensor theories. So you can reconduct this action here to some action with your scalar field as the form of before. So everything said for previous theories hold, in the sense that we have no scalar theorems and the other characteristic I've said. The most general one is, for example, the Ondersky gravity. So this is the action. Might seem very ugly, but it's the most general one that you can have for scalar tensor theories. And it leads you to some consistent second-order field equations. And it's ugly, but it just presents some complex combination of the derivatives of your scalar field. Some of them are coupled to the Ricci tensor, some of them are not, and this is just the most general one that you can have. And you can have some subcases where you satisfy the Noether theorem, and subcases in which you actually evade your Noether theorem. Yeah.
Quick question on the first part, like the f of r. I'm super surprised that you can take any f of r and just recast it into one scalar field.
Yeah.
That seems like magic, no?
But no, basically you can prove it actually very easily, in the sense that, I'm sorry I haven't written it here, but you can consider an action with some scalar field. And then when you derive your field equation, you vary your action. For example, you include, you put there two fields. You derive your action with respect to your two fields, and what you end up is that one of your fields is going to be equal to your Ricci scalar for the field equation, and you end up with this action here. I'm happy to show you even later this kind of derivation that you have. Okay, this is the Ondersky gravity. Final examples regards quadratic gravity. So in quadratic gravity, we are going to consider some quadratic curvature terms in the action, and this will make your action renormalizable in the standard quantum field theory approach. One example of this quadratic gravity is, for example, scalar Gauss-Bonnet. I'm going to show you also some more details related to this theory. We have our Einstein-Hilbert action, but here we are focusing on the coupling then between the Gauss-Bonnet invariant, I've presented already before, with some function of our scalar field, non-minimally coupled to the Gauss-Bonnet invariance. This theory belongs to the Ordensky class I've showed before. It presents no instabilities, in the sense that this is acceptable as a full theory. The coupling that we have here is the fundamental coupling of our scalar Gauss-Bonnet theory, as the dimension of a mass to the power of 2. Sorry. And this kind of theories admit hairy black holes. We have black holes with some scalar charge, and because we are satisfying this coupling between our scalar field and higher order curvature invariance. Black holes have scalar charge, while neutron stars have a vanishing scalar charge. So here we can use this theory to probe scalar fields by using black holes. Another example of quadratic gravity is dynamical Chern-Simons. And here the coupling is with this quantity here, quadratic gravity. Again, it's a bit more, let's say, complicated with respect to scalar gas Bonnet because it's not acceptable as a full theory. So you might think of it as some truncated version of a more fundamental theory, and you need to consider that your coupling is going to be, your dimensionless coupling is going to be much less than 1. Okay. So this is just an overview of all the modified gravity theories I've presented here. We are full of these theories, so I just presented the main ones. And I presented our alternative gravity theories, and now I'm going to focus on a particular example of the top-down approach in which we consider modified gravity theories, and then we recover some bounds on the new parameters that these theories provide us. And I'm going to do this by focusing on a particular source, which is which are extreme mass ratio spirals in the presence of new scalar fields. So extreme mass ratio spirals are one of the key sources for the future space interferometer LISA. We have a supermassive black hole. We have a little object that complete very complex orbits around our supermassive black hole, which are inclined and eccentric. And in particular, in the last year before the plunge, these kind of sources emit gravitational waves in the milliards frequency bands for LISA. And by tracking the gravitational waves emitted from this system, it's possible to recover the parameter of the binary system with very extreme accuracy. So with very high accuracy. So we can think about this system in general to, for example, probe the nature of the Kerr black hole and the space-time of the primary object in general. And Richard is going to focus on this point of view here, while instead I will focus on probing fundamental physics by probing the structure of the secondary object instead of the primary, and I will show you how. So if we describe MRIs in general relativity, we can see that at leading order in the mass ratio, and our extreme mass ratio much less than 1, we can consider, we have as the source term a point particle, so this is the action for our point particle. MRIs are solved in black hole perturbation theory with self-formed methods. So in black hole perturbation theory, you expand your metric tensor from a background in orders of small parameters. In self-force, these small parameters is given by the extreme mass ratio of the binary systems. And what happens at leading order in the mass ratio, you end up with these field equations for your extreme mass ratio spirals. So here has an tensor with the action of a point particle for the source term. Here I'm modifying the theoretical framework by considering a new extra scalar field in our action. And we are being theory agnostic in the sense that we don't specify any particular expression of our action. We just say that we have a new scalar field, massless, shift symmetric. This is the Einstein-Hilbert action. We add a kinetic term for the scalar field. Then we consider a non-minimal coupling between our gravitational field and our scalar field with the coupling constant alpha, which are here the dimension of a mass to the power of n. And then we have the action of the matter fields. And with respect to what I've shown here, where here it appears the mass of your secondary object, if we add a scalar field, in general, we will have a given function of our scalar field. So we modify the action in this way. We don't specify any particular coupling. But what happens is that for black hole, they will have a scalar charge that is going to be proportional to our fundamental coupling constant and the mass to the power of n. So if we specify these extreme acceleration spirals, what happens is that the mass of the primary is much larger than the mass of the secondary. So the scalar charge of the primary is going to be negligible with respect to the scalar charge of the secondary object. So basically, you have a decoupling of scales in which you have here a paired black hole and then a secondary that carries a scalar charge, which appears as an expansion of our scalar field in a reference frame of the secondary object. And here I'm going to call this scalar charge D, and it's a dimensionless quantity written in this way. And so modeling this kind of binaries, let's say it's much easier by having to modify a non-Kerr background, because thanks to the coupling of scale, what we end up to have here is just a Kerr primary. So we need to perform perturbation among a Weierstrass spacetime, which is simply given by Kerr. So this greatly simplify our descriptions of memories with scalar field. Okay, so I've given you this argument. Actually, everything has been formalized precisely in a self-force scheme in this paper here. So you simply consider expansion of your metric tensor with the extreme acceleration, and also expansion of your scalar field. And then from the general action I've written here, you vary it with respect to the metric tensor to obtain the field equation for your metric tensor. And you do the same by varying the action with respect to your scalar field. So given this, we can simplify some terms in the sense that if we stop at leading order in the mass ratio, we neglect all the second order terms. So for example, if you modify this term here with respect to the metric tensor, you obtain your Einstein tensor. Then you will have to modify this term with respect to the metric tensor, and it will lead you simply to second order perturbation in the scalar fields, which are going to be neglected. The same for varying your coupling term of the action. And the only leading term that you will have is the term that comes from varying your matter, the action of the matter fields with respect to the metric tensor. So you end up with this field equation here, and the same if you vary your action with respect to the scalar field. So you obtain a scalar field equation with this source term here. And this is very nice in the sense that, okay, we are stopping at first order in epsilon, but what we obtain are two field equations that are fully decoupled. So one is for the gravitational sector only, for our metric tensor, and the second one is for our scalar field, fully decoupled. The first one is the same that we have in GR, so this is also nice because it greatly simplifies our description. And the second field equation that we have here for the scalar field is a scalar wave equation, where we have here, we are on a Kerr background. We have this source term here, which is proportional to our scalar charge, D. And we can see that then this field equation has an universal form, in the sense that all the information of our gravity theory, which are here, of our specific gravity theory, are just enclosed in this extra parameter. And in this sense, we are being theory agnostic, in the sense that we have just one extra parameter, and then one can go and look at the specific theories that we are considering. A thing that I want to stress is that for theories that predict hairy black holes, we can find a relationship between this quantity here that I'm calling D and the fundamental coupling constant that appear here in the action. So we have this relationship, and I will go back to this later. Now, these field equations can be solved in perturbation theory with the Tucholsky approach. So basically, you consider your perturbation, and you decompose it in the frequency domain, and you can see that you can split the radial part from the angular part, so I believe you should have seen some of this already from the previous lecture. What I want to stress is that you can also consider the scalar perturbation in this way. It's again solved by with the Tucholsky approach. So this has here is the spin weight of your perturbation. So if you put it to 0, you are considering scalar perturbation. If you put it to -2, you are considering a gravitational perturbation that has to be satisfied from your perturbation for the Tucholsky equation. So what happened is that you end up with the little body spiraling around the primary, and it will emit not only gravitational waves, but also some scalar waves, which are our scalar perturbations. When we want to detect the scalar field, what happens is that we are not directly detecting scalar waves, but we are detecting the presence of the scalar field by detecting our gravitational waves. And the presence of the scalar waves simply causes an extra loss of energy. So your orbital evolution is going to be modified by the presence of this extra energy loss. And so you can compare it with your GR prediction and perform all the type of parameter estimation that you want. Okay, so here just very briefly to how to solve the field equation by focusing on a scalar perturbation. So you can see that by splitting in this part the radial dependence and the angular dependence of your perturbation, you end up with two decoupled equations, one for the radial part and one for the angular part. This is the one for the radial part, which is a master equation with a source term, which is here written as J. And you have to solve this Tucholsky equation by first considering homogeneous solution with some boundary condition. And these boundary conditions are that you want at the horizon purely going away, so nothing is coming out from our black hole. And you want also that at infinity you will have purely outgoing waves, so nothing is going to come in from infinity. So these are the boundary conditions that you impose. And then after having found the homogeneous solution, you can obtain your general solution by integrating this homogeneous solution over your source term. Okay? And with this, you find your general solution for your perturbation, and then you can compute the energy flux associated to this perturbation here. So here I've written the simple formula for circular orbits. You can go and consider also more complicated type of orbits. And what it matters here is the energy flux associated to our perturbation. I'm plotting here just to have an idea in mind of our scalar fluxes for circular orbits for different primary spin as a function of the orbital radii. And this is the difference of your scalar fluxes with respect to the gravitational one. So you can see that the difference, this ratio grows up by considering, by going to larger orbital distances. This is because the scalar emission is more dominant at larger distances. And then here you have different colors just by considering different values of the primary spin. And you have extra energy emission here because if you consider the spiral up to the flange, by increasing the spin of your primary, you can get closer to the black hole horizon. Okay, and this is a behavior, let's say, to have in mind for the scalar emission. So here I'm just putting the modeling step that you need to do for your model of Emrys with the scalar field. So the building blocks are these extra fluxes. So these scalar energy fluxes are simply summed to the gravitational ones at the leading order in the mass ratio, and they are proportional to our scalar charge. So once you did this, basically everything else will come from free from the M remodeling at leading order in the maceration, in the sense that you simply need to add this extra scalar energy emission. And then from here, you can model your adiabatic trajectory. And we call it as an adiabatic trajectory because we are considering only, let's say, the dissipative part of our spiral, which is the gravitational wave emission and scalar wave emission in this case, which is added to our gravitational one. And what happens is that you can model your spiral as a sequence of geodesics. And the fact that you have some gravitational and scalar emission leads you to a slow decay from one geodesics to another. So you can impose this balance law, which is the rate of change in time of your integral of your geodesics, your energy, and it's going to be balanced out by the energy flux from gravitational and scalar waves. And from this, the energy of your geodesics is related to the radial coordinate, and so you can obtain the time evolution of your radial coordinate and of your phase as well in this way here. So you have some forcing factor. One is coming from the gravitational sector, and one is coming from the scalar sector, proportional to our scalar charge. And from this, which is these are your ODEs for solving the Emery trajectory, then you can model your gravitational wave, and then you can start comparing this gravitational wave in GR with the gravitational wave that you have in the presence of a scalar charge. So, for example, you can compute the dephasing, the faithfulness of the two waves, and then perform some parameter estimation with a Fisher information matrix with some Monte Carlo fully Bayesian analysis. And this is the full sketch. Okay, I just wanted to say here some tools that you might use for this type of model here. So I just wanted to show the tools that are available for the model. So for black hole perturbation theory, there is the black hole perturbation toolkit. There are more, of course. I'm just brightening some. For computing, for example, your gravitational and scalar fluxes. So you have these Mathematica packages where you have geodesics and Tucholsky packages to model your spirals and to compute your perturbation and the fluxes associated to them. Right now, the Tucholsky package is implemented also for generic orbits. Yes?
Ooh.
I want to ask, can you maybe say something intuitive about the scalar emission? Like, how can we think about it?
Okay, so basically you can think about it as you have your black hole, and it's going to have some scalar field profiled around it. And this is going to have, in this scalar profile, you can think about as the scalar charge. And then, for example, you have this particle that is accelerated in the black hole space-time, and you know that a charge accelerated and it have some emission. Okay, so with the scalar charge accelerated, there is associated some scalar emission. And the most intuitive way I can think about this scalar charge is simply the scalar profile that you have around your body.
Thank you.
I can say, I mean, this is no different than normal emission from electromagnetic radiation. Right? You have charged particles, an electron, accelerated, will emit radiation, electromagnetic radiation in this case. And in this case, you have another type of interaction, it's a scalar field. And you have radiation, in this case, scalar radiation. But it's exactly the same mechanism. Basically, something accelerated which has some charge of some type of interaction emits some type of radiation.
But, I mean, should we think about it also as like waves of space-time, or like, no, I guess not?
Space-time, you have the waves of your metric.
Yeah.
While here it's just an extra
okay, something
field.
different, okay.
Yeah. And it's a scalar field.
Okay.
Yeah?
So, how can you differentiate these scalar fields from environmental effects?
this is a very good question in the sense that you, of course, are going to have some systematic problems, and it's a thing that you need to study carefully, case by case. No? For example, in this case, you might expect, for example, that their emission might be different in the frequency spectrum. And so you might be able to disentangle this effect in this sense on how they modify your waveform, on the impact that they have on your waveform. But surely you need to have, at least for my perspective, a model which takes into account both effects and to actually perform some studies to see if you're able to disentangle the effect, if you find some degeneracies, and all of these. Also, for example, for environmental effects, if you think about them as, I don't know, some accretion disk around your primary object, for example, a thing you can consider is that if you modify GR, you will expect this to be an universal modification. And for example, in this case, your scalar charge is has a precise behavior with the mass of your black hole, and you have just this relation here. So every black hole you find, if you start to have multiple events, for example, you know the behavior, how you will expect of your scalar charge with respect to this behavior here, while, for example, environmental effect might be more present in some binaries, in some not. So you can also take this point of view for the disentanglement of the two effects.
As a kind of follow-up on understanding what this scalar field is, do you have an intuitive argument why neutron stars cannot possess a scalar charge, for example, but black holes can?
So it really depends on the theory that you are considering. You have some theories in which one of them has and the other does not, and vice versa. For black holes, they are related to this Noether theorem. For neutron star, you have a modification that arises from the equation of states. I'm actually not sure on how to derive the scalar charge of the neutron star.
Yeah, so it's basically something that just rolls out of the equations of motions if you do the math.
Yeah,
or,
yeah.
Okay.
You have your theory, you have your action with the matter fields and with the coupling and the extra fields that you are considering, and then you derive how to describe your objects.
Okay, thank you.
Hi. Okay, so I have surely a super naive question that is maybe similar to the environmental question. So, like, I saw that you were talking about the waveform will be dephased and things like this, and those are some observables. So is there degeneracy, or how can you separate, like, GR with slightly different parameters and the parameters you've assumed in GR plus additional field? I guess, like, is there degeneracy, and how do you break it?
Yeah, these are, I would say these are an open current question that we have. Like, we actually need to precisely model both effects and to perform data analysis on them to see if you are able to disentangle or if you find degeneracies case by case for these things. And also you can expect that environmental effects will modify your waveform in a certain way and different from the one that arises, for example, here with the presence of the scalar charge. So, for example, the polar emission is a smoking gun effect. So I think there might be some ways in when you can precisely disentangle these things. But to have a precise answer, you need to actually do the parameter estimation, which is complex.
Okay, thank you.
Yeah. Oh, gosh.
This is also probably naive, but on that note, what if, if you have two different classes of sources, and you're trying to see, let's say you got an emery and a massive black hole, and in one of them you expect to have environmental effects, the other one you don't. I don't know if this is true, but let's assume it is. And let's say the question is what you're detecting a non-GR effect, or if it's, again, in some environment and things like that. And only one of the sources could have both of those possibilities. Do you see what I mean? So I guess what I'm asking is that a way in which we can break that degeneracy? If it's non-GR effects, it should apply to both sources.
Yeah.
And we would expect to see that deviation in both. Where if it's environmental, it'll only affect one source. Is it something like that? Is that general idea.
Yeah, this is something that you can consider if you expect, for example, that both black holes should have the charge and have this kind of effect on your binary system, while some environmental effects, which may be present or not, you can disentangle in this way.
Okay.
Of course, you will need, in this case, then multiple events.
Of different sources as well.
Yeah, on different type of sources. So, for example, for MBRIs in particular, it's a very challenging question because the rate of detection are still very, very uncertain. No? So we hope we're going to find many and disentangle all our effects, but it's an open question. Okay. So I've started with the Black Hole Perturbation Toolkit, which is a toolkit for example, easily compute your fluxes and for every time of perturbation. So there is both gravitational, scalar, also vector perturbation for generic orbits around curved black hole. There is also the curved geodesic packages. So for example, I use this to simply draw all the MBRIs that I've put in the slides. For the generation of gravitational waves, we use fast MBRI waveform, which is a LISA pipeline, and the second version of the pipeline has been released some months ago, which is developed for equatorial eccentric orbits around curved black holes. And with this pipeline, basically, it's a modular framework, and you have some different modules, for example, the trajectory packages, the amplitude packages, which are all the packages that you need to build your Tucholsky waveform. And it's easy to, let's say, modify this pipeline here in the sense that given the modular framework, what we need to do in this case, for example, is simply to add the scalar charge emission. So in order to do so, you need to modify your trajectory class, and you simply need to include your scalar fluxes, add them to the trajectory, and then everything else will come for free. So you modify your trajectory, but then your gravitational waves it's going to be given by the fast MBRI waveform packages. And then there are also some data analysis repositories that we can use once we have our waveform modeled with the fast MBRI waveform. And here just some example of repositories that you might want to use if you want to perform this kind of data analysis on fast MBRI waveform. And I think now I'm just going to present some results that then we obtain for the scalar charge. And so the first parameter estimation that have been performed on this type of signals. So the first one are performed by simply considering a Fisher information matrix approach. In this approach here, you inject the waveform with all the parameters that are here. This is focused on circular and spiral. So we have the masses of our binary, we have this primary spin, the luminosity distance of our source, the angles related to the sky localization, and the initial radii, the initial phase, and the extra parameter, which is our scalar charge. If we model our waveform, then what we need to do to perform this analysis is to compute our Fisher information matrix, which is given by the inner product of the derivatives of our waveform with respect to the parameters. Then you invert your waveform, and by the square root of the diagonal element, you can find the statistical error associated to your parameter. Okay. So we did this for a specific, there are the results for a specific circular in spiral of a MBRI prototype, where we have here a supermassive black hole with a mass of 10 to the power of 6, a primary spin at 0.9, a secondary mass of 10 solar masses. And we injected the waveform, and we varied with respect to the all parameters. So we compute these matrices for the all parameters, and then we can invert it to find the errors on all parameters. And here specifically, I'm putting the errors that was found on the scalar charge as a function of the scalar charge itself. Okay, so this is the relative error. there are two types of SNR considered. One considered low for 30 and one considered high SNR of 150. For different values of scalar charge injected, we see that we can find relative errors of the order of percent. So here we are, for example, 10%. And by increasing the value of the scalar charge, of course, the relative error decreases. Your precision on the scalar charge increase. Here it's just the fit that one can find for these relative errors as a function of your scalar charge, and also by increasing the SNR, the relative error on your scalar charge decreases. And here it's simply plotted the interval at 3 sigma that you have for the different values of the scalar charge, and you can see that it decreases with the increase of your scalar charge. So take home message, LISA could be able to measure scalar charge with an accuracy of, let's say, 10%. And these are the first results for circular spiral with the Fisher information matrix. Then there are some results also, the most recent results that we have for forecasts of LISA on how well LISA will be able to detect the scalar charge. And these are coming from a Bayesian analysis. So here I've been considering equatorial eccentric in spiral. At the time, the second version of Q wasn't released yet, so the amplitudes are computing simply with a clutch. And the analysis has been performed on some binaries prototypes. So we have here 8 different binaries. And these are the histograms of the posteriors that you obtain for your scalar charge for all the different binaries. And here, the line here is the 95% level of confidence that we have. Here, the intrinsic parameter of the binary is considered. So we consider different prototypes here, and they are relative to different intrinsic parameter of our binary system. So we can take, for example, binary number 6, where we have the typical Emery, 10 to the 6, 10 solar masses, primary spin 0.95, initial eccentricity 0.4, and a time evolution of 2 years before the plunge. So we are considering waveform with a given time of observation before plunge. Here it's 2 years before plunge. And this is the upper bounds that we have on the scalar charge. Now, for example, from this system here, you can decrease a bit the initial eccentricity, and you have a slightly worse bound on the scalar charge. The same if you, for example, consider a slightly less rotating primary spin, primary object, and so on with other type of binary. So here, for example, we are increasing the time of observations. Here, which are, let's say, the best bounds are coming from decreasing the mass of the primary. So I want to put the focus on this system here, where it's the one that is giving us the best bound on D. And it's also the one that has the lowest primary mass. And this means that it also has the largest initial radii, let's say, of evolution before plunge. And so we expect that this system here is leading us to the best constraint on the scalar charge. And we believe that it's so because we have this extra scalar emission. And the dipolar emission, the extra scalar emission is more dominant at larger distances. So here we are exploring also larger distances where our scalar emission is more dominant, and this will lead us to better constraint on our scalar charge. Okay? Yeah?
I understand how to read this graph because it's shorter.
Oh, sorry. Yeah,
Oh my God. I'm so sorry. Sorry, I was just asking about how do you read this graph? Like, the shorter it is, the better the bound, or like what's on the y-axis?
Okay, so maybe so here we are the signal is injected with a value of 0. So basically what you're performing is a test in which you assume that your signal is with a zero scalar charge, and you recover your posterior around this value of zero scalar charge.
Okay, I see.
So the smaller the error, the better the bound you can get on your new parameter here. So we are injecting the value which is compatible with GR, and we are saying which is the error that we have on these parameters here.
Oh, okay. Thank you.
Okay, cheers. Yeah.
The time is in the plunge.
Yeah.
Plunge.
Yeah, it's for example, in the first one, it's 4 years of evolution before plunge, and the plunge is considered the horizon plus a little bit, so, a very small shift. So these are all plunging memories. Okay, and the SNR is fixed to 250 for all the signal. And this gives us indeed the bound of the scalar charge when we are injecting a value which is compatible with GR. Another thing that one can do is, what if in our universe we have a scalar charge? Will Lisa be able to detect this scalar charge and with accuracy? So here it has been injected a value of the scalar charge in your waveform, which is different from zero. So it's this value here. And you can recover the posterior around your parameter in this way. This is the one that we obtain for this type of binary here. And these are the errors that are obtained, which is roughly 20% relative error on the scalar charge. Okay. So with this Bayesian analysis, basically we are injecting some simulated waveform, of course, to understand how Lisa will be able to then analyze this signal and forecast the binary parameters that we have. And we did this by varying all the parameters, and this is just the posterior on the specific scalar charge posterior. Okay. And another thing that one can do with the Bayesian analysis is to consider systematic biases, in the sense that you want to find some systematics of your model. So what you do is that here you imagine that in your universe is present a scalar charge. So you inject a template with a scalar charge, but you recover it with a GR template. So let's see. What we are asking ourselves is, if in the universe there is actually this scalar charge, but what I'm using is just a GR template to analyze all our gravitational waves. And this is just to have an idea of the corner plot that you get with the Bayesian analysis for all your binary parameters. Here we have eccentric orbits. So there is also the eccentricity. These are the intrinsic parameters, so the masses, the spin, the eccentricity, and then the extrinsic one for the sky localization and your luminosity distance. But I want to put the focus then on the intrinsic parameters here. So basically, what it has been plotted here is the posterior that you obtain by injecting with a scalar charge and recovering with the scalar charge. And you obtain all these posterior, which are these lines here on the left, by recovering with the same signal, with allowing the scalar charge and all the other parameters to vary. While in the signal, the posterior on the right, you are recovering with a GR template. So that's why the scalar charge is not plotted here, because in the second case, we are not allowing the scalar charge to vary, and it's simply set to 0 as for the GR template. And we can see that these are the posterior that we obtain instead if we analyze our injected signal with a GR waveform. And so we obtain a systematic bias around 2 or 3 signals for the intrinsic parameters. And this is something that we have to take in mind when we go to do, we want to do all these kind of studies, like the systematics of our model and the impact that they have on the forecasted parameters. So it's a very important study to have in mind. Here we are obtaining a value of 2-3 sigma systematics. Given the very small statistical error of our binary parameters with Emery, we can say, okay, for astrophysical conclusion, I would say I don't really care if I'm using a GR template, because the bias that I get on the parameters comparing with the statistical errors is very small. But actually, first of all, this might be important when you want to detect very tiny effect as the presence of the scalar charge. And also, it might be, in any case, important when, for example, you start to consider multiple events, for example, and it's a bias that, in any case, you have to have in mind when you perform these kind of studies. Okay. Another thing is that all of this has been purely theoretical agnostic, in the sense that we are constrained in the scalar charge. Here, a particular example on how the scalar charge then can be mapped on a specific theory. And this has been done, for example, for scalar Gauss-Bonnet. So I presented already scalar Gauss-Bonnet. We have this coupling term of the action here, where we have here the Gauss-Bonnet invariant, and here there is the coupling with a given function of our scalar field that we are taking to be the scalar field itself. And in this case, we can find this relationship here between our fundamental coupling constant and our scalar charge. So if we stop at leading order, what we have is this relationship. And here, mu is the mass of the secondary. So it's related, our fundamental coupling constant, it's related to our scalar charge and to the mass of the secondary in this way. And so from the posterior on D, one can obtain the posterior on our coupling constant in Gauss-Bonnet. And this is the translation of the upper bounds that we obtain for Gauss-Bonnet. I'm putting here two references line. The first one here is the most tightest bound that we have on this theory, on Gauss-Bonnet, and it comes from gravitational wave event LIGO Virgo, in particular this event here. It's providing us the best bound that we have on scalar Gauss-Bonnet, and it's a very particular event in the sense that the secondary has a solar mass of around 3.6 solar masses here. The second forecast is this is a current bound. The second one is just a forecast of this paper here for the LDK Voyager. And this is just to have a comparison with current or other forecasted observations. And so here are the bounds that we can obtain with Embry's with scalar fields, while this one is just coming from current gravitational wave observation. And I want to put the focus on a particular effect, which is the best bound that we obtain here for the scalar charge. Now the best bound is actually given by system number 2 instead of system number 1, and this is because it enters into play also the mass of the secondary object. So also the mass of the secondary object has to be taken into account, and here it's because in system 2 is smaller with respect to system 1. Okay, 3.6 with respect to 5, so we obtain a slightly better bound when we do this translation on our coupling constant for Gauss-Bonnet. Okay, in this study I've been considering just some prototypes of Embry. Okay, this is just some Embry prototypes. What one should do is, of course, to perform a paradigm estimation on exploring the parameter space that we have. And in particular, we can see that if we explore, let's say, binaries with a smaller primary mass, and we allow to go more into the Embry regime, we might obtain even tighter bound on our scalar charge, and then also on the, for example, fundamental coupling constant for Gauss-Bonnet. All right. So I think I can leave you here with the conclusion. So we have seen in this lecture an introduction on how to test general relativity with some motivation and the two different approaches that we can use to perform this kind of test. We introduce also Noether theorems in general relativity and in the modified gravity theories. And finally, we focus on a particular source for LISA to probe new fundamental physics, which is given by Embry's with additional scalar fields. this is just a particular test that we can do, and in the future lectures, Richard is going to present other sources and other type of tests that we can do with the future space interferometers. So thank you very much.
Thank you very much, Susanna. Are there questions, or did you ask everything during the lecture? Yes?
Thank you. So this is perhaps a little bit tangential, but it's related to what people were bringing up during the lecture about environmental effects.
Yeah.
So it's like one of the things that I'm studying right now, but like it's for like equal mass binaries, not errors, and also like in the inspiral regime. So the way that we're approaching that is through just like using PN expansions, and we found is like, you know, for example, like just in GR, environmental effects, like for example for neutron stars, is it comes in at 5 PN order, and if you want to like calculate the bias and compare it with beyond GR theories, like you would have to also find a beyond GR theory that has PN corrections at like comparable PN orders, and what we found is that it's difficult to find GR theories that are at, for example, 0 and 5 PN. So we concluded, perhaps a little naively, that there are, like, you know, you can't really confuse the two effects. But I don't know, like, what you think about this. Like.
So, I would say that one might be tempted to say, like, for example, for environmental effect, you have this effect of a 5 PN order, that you said, which is different. For example, the scalar emission, you have the leading one that is at -1 PN. So in this sense, I said that you have different effects on your frequency for the both of effects. But I'm not sure in this, but I would say that then when you go and model your waveform and perform the parameter estimation and recover all your errors on the parameter, and you perform the parameter estimation, I mean, I think it's something that you need to actually do in order to reach any conclusion. But this is my personal point of view. I don't know if you have other.
Well, I don't know which type. Do you know which type of environmental effect? At 5 PN, what type? So, for example, at 5 PN, you might also have tidal effects, for example, which could be confused with an environmental effect at 5 PN, for example. Another issue that I see, especially with tests that you're trying to pinpoint, oh, there's something at a given PN order. I'm not exactly sure you can actually tell at which PN order. If you see some deviation, for example, imagine that you have a deviation at, I don't know, 2 PN, and you do a test where you're adding a deviation at 3 PN, like a random PN order, you will probably also see you will measure a deviation, because your extra parameter that you're adding at 3 PN will try to fit whatever is there at 2 PN. So it's not that easy actually to know at which PN order your deviation is coming. So it's not, I think knowing something enters at the given PN order might not really be the way that you will be able to distinguish things. I believe at the end of the day, it's always going to be through some sort of model selection. You have several models. Well, at least I think that's probably the way to go. With several models, some of them will fit better the data, and over time you will build, if there are some deviations, assuming there is, you will build confidence that, I mean, it's not going to be like something, you see a deviation and you're sure that it's something, right? It's going to take probably years and years of seeing more data with that particular deviation and something like that to be able, I mean, it's exactly the way we normally, we became confident about GR, right? I mean, because we did several tests and GR kept passing all the tests, and now we believe the theory is probably very good. But it's not something that you can see with one particular test, at least that's my opinion on the subject.
Sorry, just to clarify your comment, so you're saying that, like, so in the waveform, like a beyond GR model, like you don't know for sure that it's just at 1 PN, like one of the PN orders, or?
I don't think you can tell exactly that something is coming back.
Okay.
The deviation is exactly.
Right. Oh, okay, okay. But even
you can
if
also
you...
test with where you have a deviation at another, and you will probably also detect a deviation, like a fake deviation.
Oh, okay, okay. So, like, from the theory, even if it points to a deviation of a certain p-n order, like, the effect that you measure isn't necessarily just purely in that p-n order? Like, okay, sorry. Yeah, okay.
I mean, whenever if you have a deviation, you can give whatever waveform with additional parameters,
Yeah.
whatever you do, that the additional parameter will try to fit.
Yeah, that makes sense. Okay.
Say exactly what the deviation.
Other questions? I had a very quick one. When you were comparing this vacuum TR parameter estimation and presence of a scalar field, did you make Bayesian factor comparison as well, or is it too computationally expensive or too complicated?
No. So we, let's say, I don't have the results, but we did that.
Okay.
Sorry.
Cool. No, cool. Okay.
Yeah,
So it's doable. Let's say.
You can come with the bias factor and by performing the analysis, and then you compare them.
Okay. Great. Nice. Okay, I think we can give a round of applause again to Susanna. Thank you very much. And yeah, I guess you know the drill. We have to be very punctual to the lunch at 12:30. So let's go there. And yeah, next fundamental physics lecture is on Wednesday morning, right, Richard? I think Well, yeah, it should be Wednesday morning. The next fundamental. Oh, this afternoon. Yes. Sorry. Yeah. Okay. So let's reconvene this afternoon at 5.